Well, Kurt, you're doing a double header. The second session is the use of atmospheric in-situ resources for radiation protection on the surface of Mars.
Alrighty.
So let's go ahead and load up that presentation. Thank you, Kurt.
Thank you. Let people settle down. It's always disconcerting when you get up to talk and then a whole bunch of people get up to walk out. You know, it's like
That's the nature of track programming.
it is. You know. So we ready? Are we ready to rock and roll?
15 more seconds.
All righty. All right. T-minus 10 and counting. All right, so I'm going to talk again. Kurt Chankaya. I'm, again, as a private citizen. I'm not an LLC. I'm not looking for venture capitalists. I'm just a private guy with some ideas. And I want to talk about using atmospheric resources, particularly CO2 ice, as a means of mitigation against radiation on the surface. So GCRs, or galactic cosmic radiation, is one of the most difficult issues in terms of radiation mitigation, in the sense that they have the highest energy and therefore they're very hard to shield. Now, they do cause additional risk to the astronauts in terms of elevated cancer risks. There's a lot of DNA damage that GCRs do. You can take different attitudes. Of course, Bob's position, and Bob's a physicist, he's a very smart guy, is that we just need to accept it. The risk is overrated, and we don't need to mitigate it. And that's there's a good reason for looking at it that way. There's other folks that are looking at this and saying that we can't go to Mars because of the radiation. Therefore, you need my massive propulsion system, you need my radiation protection system, whatever. And I thought what I'd like to do is you have one position where Bob's saying no radiation mitigation, which is obviously the easiest method. And it's not because Bob doesn't care if people get cancer. It's because he says the amount of resources you need to mitigate the radiation is so intense. And I thought I'd look at something. What if we could do something where we could mitigate the radiation by very large amounts on the surface, and really bring it down to levels that are almost Earth levels when you're on the surface, and kind of see in between those two. And if you could show that the impact of mitigating it a large amount wasn't intense, then you could say that, hey, this is a solvable problem no matter where we end up on the spectrum. So again, looking at the idea here is basically to build an igloo of CO2 ice around an inflatable habitat while you're on Mars. CO2 is available in basically infinite quantities on Mars. It needs to be cooled down, and it needs to be kept cool. But other than that, it's basically available in infinite amounts relatively easily. All you need is an intake valve and so forth. It's, if it's thick enough, it can reduce the radiation quite a bit, and I'm going to lay out a concept. It's just concept, so, don't sharpen the spears too much. Where you're getting about a 90% reduction in GCRs, and that's a lot, because it's a very thick igloo. And the nice thing is this is an igloo that is self-supporting, and it's made out of blocks, so you don't need to cast the whole thing. It can be made in increments, it can be made in different sizes, and it's self-supporting, so I'm not stressing the structure at any. So, just a little bit of background for what GCRs are. It's called galactic cosmic radiation because we wanted to confuse students for the rest of the time. They're really high energy particles that come from deep space. They come from all 4 pi around us in every direction. They go up and down with solar wind and sunspot cycles, because the solar wind tends to push out. If solar wind is high, then GCR is low. It kind of goes up and down and so forth. Most of them are protons, about 90%. Then you get some heavier ions, and then you get about 1% of the really heavy stuff, like iron and stuff. And that's the stuff that you look in the literature is really scaring folks, because that stuff has just got a lot of mass, it's a lot of inertia. Due to the nuclear physics, it tends to, atoms tend to interact, or nuclei tend to interact with other atoms of similar atomic weight. And so, iron is going to interact with, DNA a lot more than, say, a proton or a lepton or something. And so they're coming in, and they do a lot of damage. The iron is the stuff that is considered the biggest risk to your DNA, and it's also the stuff that's really hard to shield out. This is not something that you're going to hold out with a couple of inches of water or something like that. The shielding has got to be several feet thick. So on On the right here, we see a graph of something called the weighting factors. And the simple math is here is that radiation is measured in both issues called grays and sieverts. A gray is just energy. If I dump a kilojoule of energy, radiation energy, into a kilogram of your body, that is a gray of radiation. How much damage it does is based on the mix of the particles and their energy, and that's converted through something called a radiation weighting factor into a sievert. And a sievert is also measured in kilojoules per kilogram, but we're not creating energy. It's just a measure that certain types of particles are more damaging to our DNA than others. And the general feeling is, again, that the heavy ions and particularly some high energy protons, neutrons, have to 20 times more damaging than regular particles. And so there can be quite a bit of difference. So a lot of the radiation is not just how intense it is and how much the flux is, it's how much energy the different things have and their different atomic weights. And as you also can see by the number of different plots there is complete consensus in the scientific community about there's not. There's a lot of arguing about how important these factors are and how high they are and so forth. And we have very little data really on how GCRs, high energy particles, cause genetic damage versus high energy radiation or high flux radiation like we get from atomic blasts, of which we have a few 100,000 unwilling participants and so forth to look at. On the left here, you see a radiation plot that comes out of Dan Hassler's paper comes from the radiation assessment detector. He is the principal investigator on that. That was the radiation assessment device on the MSL that has measured the radiation level in space and on the surface. And you can see here the radiation level that comes from transit, where you have no shielding around you at all, you're not in space. And then you see from 500 days on the surface, and they're both about in the 300 millisieverts, which is not an incredible amount. We give sieverts to people in radiation treatments at hospitals and so forth, but it is not a minor amount of radiation. Over here, you see what a person on the ISS gets in 6 months. That's about 90 sieverts. This is a log scale. And down here, kind of remember this is 20 millisieverts. This is the level that a radiation worker is allowed to get in the United States. So that is a kind of the upper scale of what people will get here on Earth, or that's allowable for people to get on Earth. So shielding from GCRs requires a thick layer of material. Again, using Hassler's paper, he did an estimate of the amount of radiation mitigation as you go down in the soil. Now, obviously, no one's gone 3 meters in the soil with a radiation detector, so this is an estimate. But the important part here is that it goes up as you go in at the very beginning. With these high energy radiation, if you have just a thin layer of shielding, you end up with a lot of interactions with the molecules there and the atoms there. They spall and shatter, and they actually create more radiation. So you put up a thin layer in front of you, and you actually get more radiation behind it than if you're just standing out there with nothing. And so these very thin layers, and the thin can mean 6 inches or so, will actually make things worse. You need to get several feet in order to get the radiation down. Here he's using Martian regolith, and you have to get about 3 meters down before you get down to an asymptotic level. You can see some different ways of mitigating it, and a lot of people talk about putting soil above you. Here's a picture of another aerospace product protected from another particle from the sky, MiG-25s that the Iraqis hid from American bombs during the Second Iraq War. The order was make sure the Americans don't hit it, so they absolutely did that. They buried it. We came out there, and there were some tail fins sticking out of the ground, and they dug through it, and someone had buried a fighter plane under many feet of soil. That's about the amount of soil you would need to get this kind of protection. And the aircraft were destroyed. Now, the actual official measurement was that with a lot of spare parts and a lot of money and time, we probably could get them flying again. But they were basically destroyed by this. And fighter planes are a lot more robust than spacecraft. So burying something in a regolith is not something we want to do to an aerospace vehicle. You'd have to protect it in some way from the weight and the burden. Caves, we heard earlier today that caves are probably the ideal location. Caves have a lot of good things about them, lots of free soil to hide underneath. There are some issues with them. Caves only are in certain locations. Now, I understand that caves are in a lot of locations, so they may not be that inconvenient. But caves only come in certain locations. The other thing is that you're going into a place that is protected from radiation. Therefore, it's a very likely place to find life. only we're going to find our own life. Hey, there's life on Mars and it's E. coli. Because we're going to spread a lot of bacteria. We're going to have a lot of forward contamination wherever we're setting up humans. If we put them in a cave, it will be permanently contaminated, and it may be in a habitable place where domestic microbes may be able to spread out, especially if we seal the thing off and pressurize it, so we're kind of pushing all of our bacteria deep into the soil in the cave. We could get a real forward contamination problem. Some people may not worry about that, and they're smart people, smarter than me about these kind of things, but the Planetary Protection Program, anybody ever see the movie Princess Protection Program? Every time I hear Planetary Protection Program, PPP, I think of that movie. It didn't win the Oscars, and there's a reason. So, where did that come from? So, the planetary protection folks are probably not like you living in caves, at least until we understand more about life on Mars. So, water ice is another one. Requires, but if we're going to get water, we're going to have to mine it, and that requires some of the difficulties we talked about in the last talk. So what I did here is I took the data from Hassler's paper of both the radiation weighting factor and the level of radiation that he's showed in cruise when he's out in space and when he's on the surface. And we get about a 50% reduction by free because you're on the surface of a planet and it's blocking the GCRs from half the environment around you. But you actually get a radiation mitigation in both the radiation weighting factor and in the level, the gross level of radiation, about 30% more than just a half. And that is primarily due to the atmosphere. And so that seems to be the radiation, based on data from the surface of Mars, the radiation mitigation effects of the Martian atmosphere. And so what I did then is I took standard atmosphere, and you can see that GCR radiation coming scanning along this will be going through quite a bit of atmosphere because it's going out sideways, and the stuff that's going straight up will go through less. And you can see the number of kilograms per meter squared kind of versus a radial angle, and I averaged them, and I said, hey, it looks like on a standard atmosphere there's about 350 kilograms of meter squared of CO2 above you, and that gives you 30% mitigation and radiation. So if we were to extrapolate that by building ice, and I were to take 350 kilograms per meter squared of ice, and I'd create a layer of that, I'd get this much, go from the surface level of 640 millisieverts a day, and I'd drop it by 30% and 30%, 30%. So I added more layers, and I picked layer 6 down here, where you get down to about an order of magnitude less, 0.073 millisieverts a day. You multiply that by 365, you end up somewhere in the mid-20s. So that's, again, the 20 to 30 millisieverts a year, which is within the levels of what a human, a person on Earth, is legally allowed to expose them to, that is considered permanently safe. So this is a very low level by space standards of radiation exposure. And that ends up being about 1.3 meters thick of ice. This is not going to be small or light. And so take here in a hypothetical habitat, that's a 3-meter radius. That gives you kind of a nice big room inside, and it's 15 meters long. That's about 1,100 square feet. So it's a pretty big room in that. And you space it off a little bit, and then you have a little bit more ice on the top because there's less atmosphere. And you kind of, I just kind of rounded it to 1.25 and 1.5 meters thick. And kind of do the math, 650 tons. That's a lot of ice. That's quite a bit of CO2 ice. There's nothing lightweight about all this. Weighs only about 250 tons on the Martian surface, but it's still quite a bit. Now, how do you do this is you're going to have to make these out of blocks of ice and assemble them. So here's a kind of a more to scale diagram, what it looks like from the side and the surface. So think Roman arches, think igloos. These are self-supporting structures. They wouldn't put any weight on anything below it. They can be self-supporting as they're built up, and you can build them in blocks, just like bricks. And so it would produce quite a bit of reduction, calculated 88%, and about 90% or so. Now, let's say it takes give yourself 100 days to build this, and let's say we're building it, not robotically ahead of time, they were building it in parallel with this. And so we would have 100 days to build it where you're going, dropping the radiation that you're exposed to constantly during the construction phase. And so you end up with about an 80% reduction of the radiation exposure on the ground. Now, because most of the radiation comes in transit, you only get about a quarter reduction on the entire mission. But it does reduce it very much on the surface. Now, there's some nice things about having a very low radiation area inside. It can give the body a rest for us to recover from the exposure when we go outside on EVAs. If we get something that's a subterranean artifact, some type of drill piece, we can pull it up and examine it in our lab there without exposing it to levels of radiation that may damage whatever we pulled up. And so it's sort of a little radiation-free zone. And it brings it down to levels that are really, really, quite low by solar system standards. Is it too low? Are you trying to do too much? As I said, I'm trying to anchor the other point of the line between just take it on the chin. And you can see here again, the bricks that you're doing in order to build it. And you can see a little bit of a gap. I put a 50 millimeter gap. That is how we keep it cool. And I'll touch on that in a second. So here, this is a bit of a spaghetti chart. But here's a nominal brick size. They're pretty big. I just kind of picked that out in that it comes to about 93 kilograms of weight on Mars, which, you probably build this with some type of semi-automated forklift and so forth. But in case something really goes off the rails, quite literally, and it's still within a two-man lift level where you could muscle this brick around and put it back on where it needs to be. So this is a phase change chart of carbon dioxide. There's also water on top of it to keep you confused. But here's the solid gas line for CO2. And here is the line for solidification and liquefaction. And here's the gas liquid line for CO2, pressure and temperature. And down here you see the average daytime peak and nighttime min for summer and winter at Gale Crater. So that kind of gives you the temperature range that you're dealing with and the pressure range. This is a log scale here. So imagine if you build a bunch of forms, pressure-tight forms, where you could pump in CO2 right from the atmosphere, and you pressurize it, and it gets hot. And the nice thing about Mars is that it's generally pretty cold. So when things are hot, it's easy to cool them. It doesn't take a lot of power to pull a lot of heat energy out of something that's a lot hotter than its surrounding. 400 degrees is about where aluminum starts to soften. And so that would be a good temperature to have as a maximum. And so you pump it up to about 400 degrees Fahrenheit. And then you start cooling it, and you can see it takes about this much pumping energy, and then it takes about this much thermal energy, and you're compressing it up to about 10 bars, and you start cooling it until it liquefies, till it solidifies, and then you cool the ice down. Most of this energy is being pulled out where it's a lot hotter than the surroundings, particularly at night. And so you're able to do this relatively cheaply. Your air conditioning unit runs uphill about 20, 30 degrees, and it runs at about a 1/3, 1/4, 3 or 4 to 1 ratio, which means that a kilowatt will pull about 3 or 4 kilowatts of thermal energy out of your house. And so you can pull this with a lot less energy than is being pulled out until you get to about here. And then you got to cool this last part. And the last part of cooling the ice is probably going to be very difficult because cryogenic coolers are notoriously inefficient. It's one reason I'm not putting a power number here. I couldn't find a comfortable number to pick for what it would take to cool this last bit of really cooled ice. But the idea is you cool it down to about minus 150, which is a bit cooler than your environment, but is not super hard cryogenic. And it's below the sublimation temperature for CO2. So you can take this, as long as you keep it at minus 150, you can just plop it out there and it won't sublimate, it won't go away. So all you need then at that point is to cool it. Doesn't need to be kept pressurized and so forth. And you build, say, I calculated you need about 2,700 blocks. That sounds like a lot. If you got 27 molds and they produced 1 brick a day, you'd finish it in 100 days, which is what I estimated. And that would take about 80 kilowatts of pump energy and heat being pulled out. That's not the same as the power requirements. That power requirement's probably going to need to figure out. It may be less, it may be more. It's probably not terribly different than this because most of the heat, again, is coming out at temperatures that are way hotter than the environment that you're trying to cool it to. Whoops. So how do we keep it cool? The idea here is that I'd have a pressurized blanket on the outside and the inside. I just picked one that was I made it 50 millimeters wide, and I put 1 psi, or about 70 millibars, of argon and nitrogen. As you cool your CO2, you're going to get a lot of, the atmosphere is about 5% argon and nitrogen, and so you're going to be left with a lot of argon and nitrogen left over, and use that as a buffer gas in here. You don't want to use CO2 because it'll freeze when it runs up against your bricks here. And you put it in a little squares that are It's just a blanket that's cut off in squares, sort of like your little, the little pads that you use to package items in. And it has a aluminum radiation barrier and aluminum reflective barriers on the front and back. And I did a calculation on both the radiative load and solar load, and from the basically convective load or conductive load. You're getting a little convection cells in here. You're taking advantage of three things with Mars. The pressure's low, which, vacuum's a great insulator. The temperature's low and the gravity's low, so your convective heat load is a lot less. You're getting Grashof numbers around 14,000, which is pretty darn low. You're getting convective cells on the side. You're getting what's called a Bernard cell, this kind of hexagonal shape underneath here where it's hot inside, or, hot's a relative term. And going in here, and on the top you're getting pure conductive because it's hot on the top and cold on the bottom. And you crank the numbers, and it's about 10 kilowatts, 11 kilowatts of thermal energy I need to pull out in order to keep this thing frozen. Again, it's going uphill, so it'll probably take more power than that. How much power, I don't know. But that's not necessarily an unreasonably heavy load. So the idea here is that I'm making a pretty darn big igloo with a lot of, hundreds of tons of ice, and I'm able to form it and keep it cool with relatively reasonable power level, certainly a lot less than, say, a magnetic radiation shield or something like that. So what ifs? What if my power's lost? Is this thing going to just, collapse, blow up or whatever? It probably takes several days or several weeks for you to completely lose your CO2 shield, and it would just start to sublimate away, and it wouldn't be a catastrophic failure and give you plenty of time to fix it. What if the pressure in the insulating blanket is lost? These are built into squares. And if the square, pressure in one square is lost, you'd be able to go out and repair it. Wouldn't be a catastrophic loss. It does have some advantages in the sense that when it's all done, when it's all said and done, I can turn off the power and I can, deflate everything, let it sublimate away. When I'm ready to go home, roll it up, and then it sterilizes itself. So all the forward contamination issue I have is gone because it'll be exposed to the Gcrs, it'll be exposed to the ultraviolets, and I'll leave a nice clean, leave no trace. I'm a clean camper. What happens if it collapses on the crew? Worst case, what happens if I just, have the entire ceiling just drop on me? And it turns out that if you assume you've got a hab below it that's filled with 10 psi, which is, a reasonable compromise between altitude and so for 10 psi is about the highest humans like to live in the long term. It's producing several times more force over that area than the gravity of the weight of the CO2 ice, so it just bounce off. This would not be a catastrophe like it would be inside a cave. What do I want to do next? There are a number of assumptions here I'd like to refine in terms of the radiation mitigation, and does it exactly take 1.5 meters, takes 1 meter, and so forth. I want to try and refine some of the power systems and cooling systems and come up with a good power estimate. And I want to see if there's some type of concept we could do in order to shield in transit as well. Unfortunately, there's no CO2. There's no air in space. So in summary, basically, not getting buried down in the exact specifics of the number, can a very thick layer of CO2 ice protect you from a very large percentage of GCRs on the surface of Mars? I think that's a pretty reasonable thing to say. Can I make it in this method with a reasonable amount of power and a reasonable amount of time? And I think that's something that appears feasible. And can I keep it cool? And I also think that's something that is feasible. So it looks like a feasible way. It may not be the best way. It needs a trade study and all that kind of stuff. But it does look like it's something that could be a great way to cut down the GCRs on the surface. And that's it. So if there are any questions, and I think you raised your hand first. So,
Okay, how well is it if you, at high pressure, the CO2 is a gas as radiation protection? Because if it sublimates in that container, you still have the same amount of CO2 there.
you mean like if there's a failure?
No, just as a gas at the same pressure levels. At high pressure levels,
It's kept cold, so it shouldn't sublimate. It's a minus 150.
I get that. I'm talking about maybe not how well is the gas itself as radiation protection.
The original numbers that come from the radiation assessment detector show that it seems to give about 30% reduction. And so I'm assuming that a long column of gas is the same as a thin column of ice.
Because if you have it in those two layers, if it's still the same amount of gas, the liquid, you still have the same amount there.
Okay, I'm not sure we're on the same wavelength, so maybe we need to get together afterwards, because the CO2 is all solid in the system. It has air, has argon, nitrogen insulation barriers. Okay. Yes. Who's next? Yeah.
Hi, I think you said this actually more than once, that it was going to protect a high percentage from the galactic cosmic rays and totally from solar flares.
Yeah.
I wasn't I wasn't sure I understood the difference. Why would it protect from solar flares completely? And I have one other question after that.
Yeah, and I didn't mention that it was a comment, so it shows your reading. Thank you.
Okay.
The solar flares are very large fluxes of relatively low energy protons, and so they can be deadly if you're not shielded. But they doesn't take much shielding. If you have enough shielding to knock out most of your GCRs, you're not even going to see the SFRs. Now, the solar flare events, there was a minor one that the RAD detected, and they barely moved the needle. So the CO2 atmosphere by itself seems to mitigate it quite a bit. But if you're able to stop, it's like if I'm able to stop an artillery shell, I should be able to stop an arrow. It's another way of looking at it.
Okay, that answers my question completely. Very good. One other question/observation. You pointed out that you get 50% reduction for free just because you're building on a solid planet.
Yeah.
If you could find a cliff somewhere and build your habitat next to the cliff, wouldn't you get 75% protection for free?
You very well could, and of course that's what you get, almost 100% if you're inside a cave, which is why caves get to be
Or
very
in a
attractive.
valley, you would have close to 100% just because you have.
There's a lot of different ways to do
Yeah.
this. Yes. So.
Yeah, the Morris Homestead project is planning on doing one in one of the corners. Wants to do it in one of the corners of Valles Marineris, which would help somewhat more. I've been thinking that you'd probably want to have on your rover an ability to, if you hear that there's going to be a nasty solar storm, a mechanism to throw a few feet of regolith on top. So you'd find a place has a deep layer of regolith with a simple. There's a few mechanisms that'll lift up regolith, dust and stuff, and pile it on the top. So you'd have a rack on the top that could easily.
Yeah, this was about GCRs, not solar flares, and I'm just kind of assuming that you take it on the chin when you go out on EVAs and stuff.
Yeah.
Solar flares are, again, because of the damage potential, probably several feet of regolith is not the way to go, but a couple of inches of water or hydrogen-rich material will stop the solar flares completely.
That might be a while to collect it or to carry that much with you.
Yeah. Yeah. So. Yes.
Say, Kurt, I was wondering if you could explain why you prefer to use solidified CO2 than just using the surface material of the planet, just the soil for making.
Because that's a good question, because the CO2 is readily available. I don't need mining equipment. How much weight does it take to do all this claptrap? And, that's another estimate I need to do for next year, but, 20 or 30 forms and pumps and coolants, probably a few tons. What is mining equipment that can pull 600 tons together is probably quite a bit more. And I'd probably need to form them into bricks in order to make some sort of self-supporting structure, because I can easily form the CO2 into bricks, and that way I have a ready-made material to make something that's self-supporting so I don't put weight on my structure. That was my reasoning. And we have one more. Boy, you're in the light. Yeah, you're in conjunction, I think. Or.
Oh, man. Yeah. I'll try to make that in Eclipse. So the two questions. I think you might have covered this first one already, but did you take into account the amount of heat coming off of the habitat in terms of the amount of power required to keep the bricks cool? And then the second question was, I like the using multiple molds multiple times, but have you given any thought to making some sort of flexible substrate that you could put over the top of your hab and then kind of form the entire CO2 layer all in one rather than assembling it brick by brick?
Those are both good questions, and I think to answer the first one, the way I assumed is that the inner habitat would be insulated, down to ambient temperature. So I just was using the ambient daily temperature cycle as the heat load going inside. That's what I meant about refining the assessments for next year. In terms of making one giant mold, it's probably going to be really heavy. It's not a nice shape. It's big, and so forth. And so the idea of using a number of smaller molds that are in a more geometrically friendly shape, I figured was lightweight. Now, 27 of those size shapes, is that the right answer? Again, a little bit of thought needs to go into it, but that was the reason I had. So,
Last question, Kurt.
When you lower the temperature of the atmospheric gases, does the CO2 separate out on its own, or do you need to pre-filter it from the argon and nitrogen?
That's a good question. What I am assuming is that the liquefaction temperatures of argon and nitrogen are way below that of CO2. So the CO2 should come out on its own. Now, you do have traces of carbon monoxide. Does that end up in the ice and weaken it, or does it just an inconvenience? And so I'm just assuming it'll come out reasonably well and that I don't have a lot of carbonation, no pun intended, of the argon and nitrogen into the CO2 liquid. That's something I need to look at, but I don't think it'll absorb 5% by volume, which is what the atmosphere has. But how much carbonation I get of those trace gases is an important fact that I kind of skipped over in all this, and I just need to look into that more. So,
Nice utilization of handy resources. Thank you, Kurt.
all right, thank you.